Recording is on.
All right.
Yeah, so the other big thing, and this is where we start caring, computer processing of statistical data in 1957 with the creation of Fortran. By the late 1960s, widespread mainframe university computers offer the possibility to construct old and new graphic forms by computer programs. This is where we start saying, oh, that's what we do. So here's some examples. This was a piece from the Comprehensive Theory of Graphical Symbols and Modes of Graphic Representations by Jacques Bertin. This guy, who, to be fair, might be dead by this point. That's a pretty long time ago, but could still be alive. Let's look. He passed away in 2010, so after this paper was written. But like, you can see that he's starting to categorize. He's categorizing like graph things. This is one of John W. Tukey's improvements on histogram on analysis of counts, tail values, hanging rootgram, a hanging rootogram. This is one of the things he developed. Called a hanging rootogram. John W. Tukey made ginormous advances in the field of data visualization. Just enormous, and algorithms, and brilliant guy. Initial development of geographic information systems, GIS, combining spatially referenced data, spatial models, and map-based visualization. Example, Harvard Laboratory for Computer Graphics and Spatial Analysis, CIMAP, producing isoline, chloropleth, and proximal maps on a line printer. So we start having GIS systems to start actually having computers crunch data. Very interestingly enough. So we're at an intersection here of computer science. No, okay. We had an intersection of computer science research, software tools, C language, Unix, at Bell Laboratories and elsewhere, developments in data analysis, EDA, psychometrics, etc., and display and input technologies, pen plotters, graphic terminals, digitizer tablets, the mouse, etc. Additional themes. We have various visual novel representations of multivariate data, Fourier function plots, faces, star plots, and clustering and tree representations. Development of various dimensional reduction techniques, multidimensional scaling, and correspondence analysis, providing visualization of multidimensional data in a 2D approximation. This starts getting really important because we start dealing with more and more data in more and more dimensions, and we need a way to compress it down to something that's visualizable. We get animations. That's really important. We can start animating things, and that opens up a lot of doors when I can like GIF it, you know. And perceptually based theory and experiments related to how graphic attributes and relations might be better ready to convey the data visually. We start doing experiments on how to do visualization. We start actually treating visualization as its own science rather than like as an aside. That's really important here. And now we get into the present, 1975 to present, but present really means 2000, to be honest. It doesn't actually mean present. We're not at present. We've advanced so much farther than this since then. It's kind of funny, actually. He starts by saying it's hard to provide a succinct view of the most recent developments because it is so varied, has been so fast across such a wide range of disciplines, and because we haven't got to see which ones are the most important yet. It's hard for me to say which ones are like really matter because we're in the middle of it and we won't see for like another couple of years. But later we'll do more work. Maybe. I don't know. We haven't published another paper or updated anything, so maybe we won't. Some standouts though. Development of highly interactive statistical computer systems. Initially, this meant large command-driven, directly programmable systems, APLS, as opposed to compiled batch processing. So we're starting to be able to interact with things. And we're starting to interact with programming languages to kind of recompile things on the fly. New paradigms for direct manipulation of visual data analysis, linking, brushing, selection, focusing. So we can start manipulating data on a computer. Like once we've graphed it, we can start manipulating it to like see certain things, you know, like you do in Excel. New methods for visualizing high-dimensional data. The Grand Tour by Asimov, Scatter Plot Matrix by Tukey and Tukey, parallel coordinates plots, spread plots, invention or reinvention of graphical techniques for discrete and categorical data. The application of visualization methods to an ever-expanding array of substantive problems and data structures, and substantially increased attention to the cognitive and perceptual aspects of data display. So we even started just talking like how we're like doing computer monitors and stuff. We also have new fundamental technologies, large-scale statistical and graphic software engineering, both commercial, SaaS, and non-commercial, Lisp, BAT, and the R project. These are significantly leveraged by open source standards for information presentation and interaction, Java and TCL/TK. We are far beyond that at this point. We went through all those. We did R, we did matplotlib, and now we're on, I don't know, bokeh and all sorts of shit. Probably we're far behind that. I haven't really been paying attention to the field of data visualization. Looker's doing interesting stuff. We have Tableau. Extensions of classic linear statistical modeling to ever wider domains, generalized linear models, mixed models, models for spatial geographic data, and so forth. This guy never really talks about machine learning, but that's really big lately, if any of you, noticed. Vastly increased computer processing speed and capacity, allowing computationally intensive methods, bootstrap methods, Bayesian Markov, multi-chain Markov models, analysis, etc., to access to massive data problems measured in terabytes. Lol, JK terabytes. And real-time streaming data. Advances in this area continue to press for new visualization methods. Yeah, so you can tell that we're a bit beyond this. Measured in terabytes. That's the impressive thing at the time. I think what? Now where it's impressive if you could now it's impressive is like zettabytes. So here I just show some examples of some multidimensional contingency tables. So in the 1890s, some initial specialized techniques for visualizing such data were developed. This is the fourfold display, where sex and no, yes, no, yes, as just a way of like displaying multidimensional data, because we're displaying sex, admission, and things. So it's three-dimensional data we're displaying in a two-dimensional plane. Association plot. So this is not the association plot that Cohen did. I found it. It was on ResearchGate, and I hadn't thought about like screenshotting it. But this, you can see it just is like the association between eye color and hair. So brown eye color is heavily associated with the black hair color, but it's negatively associated with the blonde hair color. So we're mapping three-dimensional data again. This is a Mosaic Plot by Hartigan and Kleiner, mapping days, weeks, and programs. So what programs come on at what times and what weeks. So like how much space programs will take up based on things. Oh, CBS, ABC, NBC. So it's actually four-dimensional data we're mapping here. We have dynamic. We get into dynamic graphic methods. The first general system for manipulating high-dimensional data was Prim9, developed by Fischler, Friedman, and Tukey. Notice Tukey keeps popping up. Tukey keeps popping up. Providing dynamic tools for projecting, rotating in 3D, isolating, identifying subsets, and masking data up to 9 dimensions. By the mid-1980s, as workstations display technology became cheaper and more powerful, the software of dynamic graphics became more widely available. Max Payton and Xgobi. By 1990s, a number of these data were brought together to provide more general systems for dynamic interactive graphics, combining data manipulation and analysis in a coherent, extensible computing environment. List Stat and its progeny, Arc, Cook, and Weisberg Vista Young provide an easily extensible object-oriented environment for statistical computing. He also talks about R here. I think we're a bit beyond that. We now have things like Tableau, and we have companies just literally providing new visualization libraries. Power BI, if anyone uses that ever, at any point. I think Google has its own thing too. Here's a tree map. Tree maps were, I think, also developed by Tukey for space-constrained visualizations of hierarchies. No, they're Ben Schneiderman. Using nested rectangles, size proportional some numerical measurements of the node. This is not Ben Schneiderman's thing. This is I just thought a really good thing to express what a tree map is good for. It is the GDP of a country by resource, and you can see that it sometimes break things up by specifics. So like this is like their metal production. They have the kind of thing down here at the bottom. Here is their like grains. They have raw sugar, rolled tobacco, gold, petroleum. Here is table lens, focus, and context for larger view tables. You can expand rows and columns to see details while keeping surrounding context. This is an example of a data visualization tool called table lens. This is Xgobi, a spate of development and public distribution for highly interactive systems for data analysis and visualizations. And you can see that you can like change things. This is like the kind of origin of like Power BI and Tableau. Summary stuff. Historical events by their nature are typically discrete, but marked with dates or ranges, and some dates numeric textual classifiable descriptors. Among the first to recognize that history could be treated as data and portrayed visually is Joseph Priestley, developed the idea of depicting lifespans of famous people by horizontal lines on the time scale. We talked about this earlier. Priestley's graphic representation of time. This is just him talking about, like, why does this matter? This whole thing that I just went over, this history of things. Priestley's graphical representation of time and duration, apparently influenced by Playfair's introduction of time series charts and bar graphs. So Playfair, remember that he was a guy we said was like the father of many modern graphic things like bar charts, time series, plotting, and stuff. British statisticians were not impressed. Historical events and statistical facts were seen as separate rather than as data arrayed along the time dimension. Historical events was not, they didn't see historical data as like being statistically relevant. Alfred Marshall, though, in 1855, argued that the cause of events could be understood by these statistics displayed to historical curves, time series graphs. Here we get to the graph again that we showed at the beginning, but here we map North America and Europe on as different colors. And it just kind of follows the thing that he goes here. The peak in Golden Age is nearly as high as that as the present, but this probably just represents an underrepresentation of most recent events. A decline in Europe following the Golden Age was accompanied by an initial rise in North America, largely due to popularization, e.g. textbooks, and significant application of graphical methods, and a steep decline as mathematical statistics held sway. And then a lot of the data viz people ended up being from America because Tukey did so much work and Tukey was American. And also the work at Xerox Labs and Bell Labs were all American. Like, America was just at the front of computing technology. Therefore, we were at the front of the high dimensional visualizations. Here is a mosaic plot that he does of like what subjects people were covering over time. You can see that it's really early on. It's physical. I don't know what the shading here means. If someone can figure out what the shading here means, I'd appreciate it, but whatever. I think this might be like how much presence there was, like how hard shaded. How many advancements? I don't know. It might correlate to this graph. But you can see that mostly it's physical. We start getting a little mathematical. Then we're getting like really human. We start doing like a lot of sociology work. And then nobody cares about human anymore. And it's all mathematical in terms of advancements. In terms of subjects of like what we're doing here. Based on the data they collected, which, granted is probably incomplete. Here's by their advancements, what the advancement was mostly in. It's mostly in maps. Maps advancements usually affect physical things. Diagrams aspects mostly affect mathematical things, and technology mostly affects mathematical things. Human, not so much. Human is mostly affected by diagram and aspects, which, this kind of makes sense. Mathematical don't really care about advancements in mapping technology. And then one last thing is, one of the points of this is just to try to understand what people were thinking at the time. And they talk about Playfair's time series graph of wages and prices. He wished to show that workers were better off at the end of the period shown than at the earlier time. Presumably, he wished to draw the reader's eye to the narrowing graph between the bars for prices and the line graph for wages. With this graph, he says, if you look closely, it's actually different than what Playfair seemed to think. It appears that wages remained relatively stable, while the price of wheat varied greatly over time. The inference that wages increased relative to prices is indirect and not visually compelling. And he makes an argument that basically Playfair, while the graph was cool, doesn't really illustrate his point very well. We cannot resist the temptation of Playfair helping hand here by graphing the ratio of wages to prices, labor cost of wheat, but is as shown to the left. But this would not have occurred to Playfair because the idea of relating one time series to another by ratios, index numbers, would not occur for another half century due to Jevons. He's like, well, but if you graph this in another way, you actually see that there is a relationship, but Playfair wouldn't have thought to graph it this way. And then here where he talks a little bit about Galton's graphs, and this is Galton graphing the height of children to the height of their parents. And he's like, and here's how Galton tried to do the correlation diagram of an ellipse of equal frequency. But if you do an actual regression, the lines look a lot weirder. The lines are a lot less correlated. He kind of got his data wrong when he drew the correlations. And that mostly comes from a desire to just be like perfect, like draw a circle and stuff. Anyway, that's my last slide. That's kind of a summary of the paper, a history of data visualization.
That was awesome, man. Thanks for walking through it. It's really cool. I I was, yeah, woo, claps and applause. I was most surprised about Florence Nightingale. I had no idea that she was so informational or so important in graphs.
Yeah, there's a lot of the stuff during that golden age period is where you get like I think the prettiest hand drawn graphs. Like people just like because you don't have a formalization, so people don't really have rules for how to do it, so they just try things. So you get things like W.D. Du Bois doing stuff, like where he just maps things upside down from like kind of how you would normally read it and stuff. I
Yeah,
think there's a lot of good stuff.
that the first W. Du Bois graph was really cool looking too.
Mhm. There's also, I think, a lot lacking. My biggest problem with this paper is it doesn't really relate. It just kind of just talks about like this happened, then this happened, this happened. It doesn't really relate it historically to anything else, which is something I tried to kind of do in my talk. But I didn't really do enough like I need to do more research, to be honest, on like how things related a little better. But like I think there's like a lot more to grasp of like what else in science was going on at the time. Why were everyone interested in transportation all of a sudden? Like what advances in other things like made this relevant?
You needed to write another paper.
Yeah, I need to write another paper on this paper where I reference this paper a lot and be like, hey, so like, and like, not gonna lie, his website, I'm gonna link it again, is actually pretty good as a source of like some graphs people did. Like, he actually collected a lot of shit. And it actually has a lot of like pictures as well. He includes like pictures and like biographies and all sorts of stuff on the people he's like talking about here, which is really interesting. But
That was really awesome. Wow, I have to dig into it. That looks fun. Yeah. No, this reminds me so much of Edward Tufte's work, and all the work he put into trying to understand how to make beautiful data visualizations.
yeah, and this is really just like how we got to where we are. And it's kind of I think it's kind of dry. It's a lot of less like names and dates and people inventing things without a lot of context, which I think is unfortunate. But I still think it's interesting to just kind of understand some of these big landmarks, like Galton, how Galton is read. You just look at how much Tukey did. You're like, oh wow, Tukey's really important.
I think it just goes to show you that it really is individuals like that catapults our understanding of the world.
I mean, one guy he didn't really mention in here who was really important to this whole thing would have been what's his name? The guy who did the demo of
Engelbert.
Mm-hmm. It doesn't mention Engelbert.
Doug Engelbert, yeah.
Doug Engelbert is really important to a lot of advances that enabled a lot of this.
Oh yeah, he the mother of all demos is that. Definitely, if y'all haven't watched the mother of all demos, definitely worth a watch.
So, did you all find this interesting as an overview? I'm curious. Oh, I think we can stop the recording too.
Yeah, I'll stop the recording. Again, I want to thank everyone so much for being here, and please contact Max Rye to sign up to speak. All right, I'm going to stop it now. Thanks.